Welcome back to your personalized deep dive. Today, we're taking a look at a piece of technology that failed so spectacularly on the public stage that, well, most people just wrote it off entirely.
Right. They completely dismissed it.
Yeah, exactly. Because we usually have this very, rigid definition of success when a massive new tech product drops. A model is released, it gets scored on a battery of tests, it lands somewhere on a public leaderboard.
And the industry basically decides right then and there if it's a triumph or a complete disaster.
Right. It's so binary. But what if the biggest, the most heavily criticized flaw in a system was actually its most valuable asset?
Yeah.
Because that is our mission today. We are looking at a July 11th, 2026 article from Tech-Reader magazine.
By Aaron Rose, right?
Yes, by Aaron Rose, and it's titled "The Defect Is the Superpower." And I have to say, the core of this story just completely flips our understanding of what it means for an artificial intelligence to fail.
It really does. It challenges this whole, this binary way we evaluate technology. We are so conditioned to look at a benchmark score and just see a final verdict.
Like, it's the absolute truth.
Right, rather than seeing it as a measurement of just one very specific context.
So the inciting incident for this whole conversation is the release of xAI's Grok 4.5. When the benchmark verdicts came back for this model, the results were, they were a wild mix.
They were all over the place.
Yeah, it had the best tool use capabilities on the entire market. It ranked 4th overall on raw intelligence. But then there was this one jaw-dropping statistic just sitting in the middle of the report. It had a 54% hallucination rate.
Which is massive. 54%.
54%.
Sure.
Naturally, the industry, the critics, and, the people who watch these leaderboards like hawks, they immediately labeled this an obituary-level failure.
Of course they did.
A model that is confidently wrong more than half the time seems like an open and shut case.
But if we connect this to the bigger picture, science actually has a very long, a very forgiving memory for these kinds of quote-unquote failed experiments.
Oh, absolutely.
We tend to forget that some of the most paradigm-shifting discoveries in human history started out as catastrophic errors in a lab. They were failures, but only in the context for which they were originally designed.
Yeah, and the article brings up some incredible historical examples of this phenomena. Like, take Alexander Fleming in 1928.
The penicillin story.
Right. So he comes back from vacation, looks at his petri dishes where he's been, cultivating staphylococcus, and sees they are completely ruined by this invasive, fluffy white mold.
Just contaminated.
Contaminated. And the standard operating procedure for any bacteriologist on the planet at that time was to toss contaminated dishes straight into the incinerator.
Just get rid of them.
Get rid of them. But Fleming pauses. He notices the mold is actually secreting something that is dissolving the bacteria around it. That ruined dish was the discovery of penicillin.
Or jump forward to 1968, you have Spencer Silver at 3M.
Oh, this is a great one.
Right. And his specific job is to create a heavy-duty, ultra-strong adhesive for the aerospace industry. Instead, he synthesizes a glue so incredibly weak and, useless, that it barely holds two pieces of paper together.
You can just peel them apart.
Without tearing anything. It's a total defect for aerospace. It literally sits in a drawer for years. He keeps pitching it to different departments with zero luck.
Until someone needs a bookmark.
Exactly. A colleague realizes it's the perfect weak adhesive to keep paper bookmarks from constantly falling out of his hymnal at church. And suddenly, the world gets Post-it notes.
My personal favorite, though, is Percy Spencer in 1945. He is an engineer working on military radar systems. And he's standing near a radar magnetron, which is essentially this high-powered vacuum tube that generates the microwave frequencies needed for radar.
Highly specialized equipment.
Highly specialized. And he notices that the peanut cluster chocolate bar in his pocket has completely melted into a mess. Now, he doesn't file a malfunction report about the radar emitting dangerous heat.
He sees an opportunity.
He realizes he's looking at a revolutionary new way to agitate water molecules and heat food. Suddenly, we have the microwave oven. So for you listening right now, this is the mental journey we are going on today. What happens if you take Grok's 54% failure rate out of the consumer benchmark context where it is undeniably a massive liability and you drop it into a research lab?
Because to understand why that failure is so valuable in a lab, we first have to understand the mechanics of the failure itself. We have to look at how large language models actually hallucinate. because it is not what most people imagine when they hear the word hallucination.
Okay, let's unpack this. Because when we hear that an AI is hallucinating, I think the natural assumption is that the computer is just, glitching out, spitting out random garbage, or crashing.
Like it's broken in a very obvious way.
Right. But when AI hallucinates, it doesn't sound like a toddler babbling nonsense. It sounds like that one incredibly smooth-talking friend who confidently gives you completely wrong directions to a restaurant.
That is exactly what it feels like.
They aren't stuttering. They aren't guessing or saying they aren't sure. They are looking you dead in the eye, speaking perfectly clearly, and sending you 40 miles in the wrong direction.
Exactly. LLMs do not hallucinate randomly. They don't output scrambled code or gibberish. As the article points out, they produce what we can call adjacent truth.
Adjacent truth. I like that.
It is fluent, it is highly confident, and it lacks any internal awareness that it has departed from reality. At a technical level, the model is simply doing what it always does, predicting the next most mathematically plausible word or token based on its training data.
It just happens to be predicting a sequence that is factually false.
Exactly.
The examples in the text really bring this to life, too. If you ask a hallucinating AI for the capital of Australia, it doesn't give you a random word like Oslo or like banana.
No, it says Sydney.
Right, Sydney. It picks the largest, most famous, most culturally obvious answer, which just happens to be entirely wrong, because the capital is Canberra.
Or it will confidently tell you a historical event happened in 1943 instead of 1945.
Yeah.
Because 1943 often appears in similar contexts in the training data.
Ah, so it's a statistical proximity thing.
Yes. It will attribute a 16th century quote to Christopher Marlowe instead of William Shakespeare. It'll swap Venus for Mercury when discussing planetary orbits, or Michelangelo for Da Vinci when discussing Renaissance frescoes.
So the error isn't random noise.
No, it has texture. It makes logical sense if you aren't paying close attention.
And that specific signature, the fact that it is confident, naturalistic, and adjacently wrong, is exactly what makes a hallucinating model a total nightmare for an end user.
Oh, it's incredibly dangerous in the wrong context.
Right. If someone is using an AI to draft a legal brief or summarize a medical journal, adjacent truth is dangerous. But from AI researcher, that exact same signature is incredibly valuable.
Which brings us to a fundamental logistical problem in AI research right now. Let's say you are a developer and you want to build a digital guardrail. You want to build a secondary system that detects these AI hallucinations and stops them before the user ever sees them. To train that detector, you need a massive, massive volume of confident wrongness to use as your training data. Your detector basically needs to learn what a lie looks like.
Wait, so if I want to train a digital guard dog to catch lies, I need a massive library of very specific, high-quality lies.
Yes. You need thousands and thousands of them.
How do researchers normally get that data? Because finding thousands of perfectly crafted false statements sounds like a logistical nightmare.
It is. Historically, there are 3 ways to build this data set, and the article argues that the first 2 are just deeply flawed. Method 1 is human-generated synthetic data.
You literally pay human beings to sit down and write out lies.
Yeah. Plausible-sounding wrong answers across thousands of different topics.
That has to be incredibly slow. And expensive, considering you'd need, experts in various fields to write believable lies about quantum physics or constitutional law.
The cost and the time are huge hurdles, definitely. But the bigger structural problem is that this method is bounded by human imagination.
What do you mean?
Well, a human author trying to construct a wrong answer has to conceive of the failure mode in advance. They can only invent the errors their human brain can think of.
Oh, I see.
The reality is, the human imagination has a much lower ceiling than the bizarre, emergent ways a complex AI model actually fails in the wild. Humans just aren't weird enough in the same specific way. An LLM is weird.
We don't make the same mathematical leaps a computer does.
Exactly.
So if humans are too slow and too predictable, we move to method 2, code-generated synthetic data.
Right.
Instead of people writing lies, why not just use code? Can't we use random number generators or, distribution scripts to swap out facts, scramble names, and mess with the data at scale?
You can, but that creates uniformly random noise. Real AI hallucinations, as we just established with the Sydney and Oslo example, they aren't random. They cluster by domain. They vary based on how the user's prompt is framed. They have systematic biases that no random number generator can ever replicate.
Because it's too uniform.
Exactly. If you train a hallucination detector on uniform code-generated noise, it becomes an expert at catching uniform noise. But when you put it into a real-world production environment, it's going to face the shaped, textured noise of a real LLM, and it will just fail to catch it.
So training a detector on random code-generated data is kind of like practicing for a chess tournament by playing checkers.
That's a perfect way to describe it.
Sure, there's a board and pieces, and it feels like a strategy game, but the mismatch in the actual mechanics is the gap where everything falls apart.
The detector is prepared for the wrong game entirely. It's looking for obvious structural errors, not the smooth, adjacent truths of a language model.
Okay, so if human imagination is too limited and code generation is too random, researchers are basically trapped. They need something that lies exactly like an AI, but does so naturally and at an industrial scale.
Which brings us back to the 54% disaster.
Here's where it gets really interesting. This is where we look at the third method for building this data set.
Okay.
Production model synthetic data. And this is exactly where Grok 4.5 steps onto the stage, not as a failure, but as the solution.
What's fascinating here is the mechanics of how they actually utilize it. Grok 4.5 is a real frontier-class model. It has a complex internal world model. When it makes a mistake based on its own training gaps and its own confident leaps across uncertain terrain.
No human author and no random script can simulate that.
Exactly. The wrongness is naturalistic because it is genuine.
So how does a research team actually capture this? Because the article lays out the pipeline, and it's quite a process.
It's a massive undertaking.
You take your high hallucination model, in this case Grok, and you run it at massive volume across whatever target domain you care about. You just let it answer thousands and thousands of prompts, knowing it will fail frequently.
Right.
And you save every single session to a massive JSON file.
And for anyone unfamiliar with the term, a JSON file, which stands for JavaScript Object Notation, is essentially a highly organized text file that software can read very quickly.
It's not just a messy Word document.
No. It structures data into pairs. So instead of a messy document, the computer gets clean labeled categories.
So for every interaction, the system logs 4 specific things into this file. The question that was asked by the user, the answer the model returned, the actual ground truth label so we know the real fact, and a flag indicating whether the model's answer was a hallucination.
And you run this process enough times, and suddenly you possess the absolute holy grail for an AI researcher. A labeled, machine-readable data set of confident, naturalistic, wrong answers at scale.
Wow.
You then feed this enormous data set into a separate, lightweight classifier model. This classifier isn't a conversational AI. It isn't trying to answer questions or write poetry.
Its only job is to analyze text.
Yes, and recognize the unique mathematical signature of confident wrongness.
But how is it doing that, though? How does a piece of software spot a lie if the lie sounds perfectly natural to us?
It looks for statistical patterns in the language that human eyes just miss. When an LLM is hallucinating, the probability distribution of the words it chooses often looks slightly different than when it is retrieving a solid fact.
So there's a mathematical difference underneath the text.
Exactly. The lightweight classifier learns to spot that discrepancy. It's essentially learning the AI's poker tell.
It's learning what a lie looks like when the lie is wearing a suit and tie, speaking fluently, and expecting to be believed.
That's spot on.
The defect literally becomes the curriculum.
It forces us to rethink model utility altogether. The brokenness isn't a bug in this scenario. The brokenness is the primary feature you are harvesting.
But I'm sure anyone listening who uses AI daily is probably thinking the exact same thing I am right now. Why go through all this trouble, specifically with Grok?
Right, there were so many other models.
We have ChatGPT, we have Gemini, we have Claude, we have Microsoft Copilot. These are incredibly powerful systems. Why can't I just take one of those models, run it in an adversarial mode, and prompt it to hallucinate for me? Like, hey, Claude, give me a confidently wrong answer about the French Revolution.
This raises an important question, and the article argues that the answer is the single most crucial sentence in the entire piece. You cannot use those other frontier models to generate this data because they have been overly aligned.
Aligned. Let's define that, because alignment is a huge buzzword in tech right now. We're talking about safety training.
Yes. Models like Claude and ChatGPT have gone through extremely rigorous post-training processes. One of the main ones is RLHF reinforcement, learning from human feedback.
So humans reviewing the outputs.
Right. Humans read the AI's outputs and give them a thumbs up or thumbs down, literally training the model on what behavior is rewarded. They also use constitutional AI, which involves giving the model a hard-coded set of rules, or a constitution, that it must check its own answers against before speaking.
And the entire goal of that massive alignment pipeline is to eliminate confident wrongness.
Exactly. And they succeeded.
They really did succeed. But that success created a bizarre new problem for researchers.
Yes, because when those well-aligned models don't know an answer today, they don't confidently lie, they hedge.
Yeah.
Their safety training kicks in and they say things like, I'm not entirely certain, but, or based on my current knowledge base.
Or you may want to verify this information.
Exactly.
And that hedge is a massive tell. It's a dead giveaway that ruins the data.
So what happens if you try to force Claude to be wrong? You write a prompt saying, role play as a model that is confidently wrong. Claude will follow your instructions. It will give you a false fact. But Claude knows it is role-playing.
It's acting. It's doing community theater. It's putting on a costume of a broken AI.
Precisely. And the mathematical signature of performed wrongness is fundamentally different from the signature of genuine, oblivious wrongness.
Because the model state is different underneath.
The probability distribution of the words is completely different when the model is acting. If you use that performed data to train your lightweight classifier, you don't build a hallucination detector.
You build a detector that is really good at catching an AI that is play acting.
Exactly.
So the superpower here is that Grok's errors are not performed. It isn't acting. Because its training, for whatever reason, didn't successfully eliminate this specific failure pattern, it can naturally produce the exact data researchers desperately need.
The rigorous safety alignment on Claude and ChatGPT actually created a capability ceiling.
And Grok simply bypasses that ceiling because it lacks that specific polish.
That is the structural distinction that really matters here. Grok isn't necessarily more capable in a broad, general intelligence sense, but the other models were explicitly trained out of the capability that this specific research use case requires.
The defect that the industry is mocking is currently the only version of this capability available at a massive production-level scale.
It's incredibly ironic, honestly.
I buy the logic. The mechanics of the pipeline make complete sense.
Yeah.
But hold on. We have to look closely at this 54% hallucination rate.
The elephant in the room.
Right. Is that number even real? Because we all know how the internet works. People love a clickbait headline. And a 54% failure rate for a major tech release sounds almost too perfectly engineered to generate outrage. How do we even know that stat is accurate?
To the author's credit, Aaron Rose addresses this head-on in the piece. The caveat is that the industry really doesn't know the provenance of that 54% number.
We don't know where it came from.
As the article states, it appeared in a headline, it got aggregated across social media, and that's about it.
So we don't actually know the benchmark methodology. We don't know what specific test set they used or how they mathematically scored an answer as wrong versus partially correct.
We don't even know if that number reflects the actual released production model, or if it was just an early, unstable training checkpoint that leaked to the press.
It could be precisely right, it could be directionally right, or it could be significantly off.
But the author argues that the exact number doesn't actually matter for the premise, does it?
Right.
It doesn't dismantle the thesis at all. The core argument doesn't live or die on the integer 54. It lives on the shape of the failure.
The quality of the errors.
Exactly. As long as there is a production model out there generating naturalistic, confident wrongness at a meaningful scale, the research application exists. Whether the rate is 54%, 40%, or 60%, the fact remains a model producing genuine adjacent truth without hedging is a tool you can use to train classifiers.
It really highlights how badly the industry's obsession with benchmark framing served this entire story. Everyone immediately treated it like a horse race.
Who is the smartest? Who is at the top of the leaderboard?
Who has the lowest error rate? The conversation was entirely static and, binary.
In doing so, the industry largely missed the forest for the trees. Very few people stopped to ask the much more interesting question.
Which is?
In what specific specialized context is this unique failure profile actually a massive advantage?
So what does this all mean? If we zoom out and look at the whole picture we've painted today, the core lesson for you, the listener, is that benchmark position is not destiny.
It really isn't.
A leaderboard ranking is just a starting point. It's a static measurement of one type of utility. The worst-ranked model on a consumer intelligence leaderboard might be the single most valuable tool in a back-end research lab.
It is a reminder that context completely changes the definition of utility.
Right.
The defect and the superpower are often the exact same thing. You just have to figure out which lab you need to walk it into.
Just like Fleming didn't throw out the moldy Petri dish, and Spencer Silver didn't throw out the weak glue, researchers shouldn't throw out the hallucinating AI. They should look at the shape of the defect and ask why it's interesting.
And if we bring this back to a human level, it leaves us with a really fascinating thought to mull over.
Oh, absolutely.
Think about your own life, your own work, or the systems you rely on every day. We all have processes that fail, or recurring defects we spend all our energy trying to eliminate.
Right. The things that drive us crazy.
What if you stop trying to fix it for a second? What is a defect or a recurring failure in your own process that you've been trying to eradicate? Well, that might actually be the exact data you need to build your next big breakthrough.
A perfect question to end on. A failure might just be the curriculum you didn't know you needed. Thank you all for joining us on this deep dive. We'll catch you next time.